Hey everyone, and welcome. Today, we're going to tackle the unit circle. And first things first, I want you to completely forget the idea that it's just some big chart you have to memorize for a test. We're going to see it for what it really is. This incredibly elegant solution to a really important problem in math.
And that is the core problem, right there. You know, the trigonometry we all learn at first, the stuff with right triangles, it's great. But it's got a hard limit. The angles inside a triangle, well, they can only ever add up to 180 degrees. But the world around us, it's full of things that repeat, that cycle over and over and over again. Think about sound waves, electricity, even the seasons.
So how do we do it? How do we take the beautiful logic of triangles and just stretch it, make it work for angles beyond 180, past 360, and even into negative numbers? Well, that's exactly the question we're going to answer.
Now, don't get me wrong, SOHCAHTOA is a fantastic tool. It gives us this really neat way of thinking about sine, cosine, and tangent as just ratios of a triangle's sides. But, it's fundamentally trapped inside that triangle. We need a way to break out.
Okay, so here's the absolutely brilliant idea. What if we take our right triangle and we sort of trap it inside a circle? And not just any circle, but a very specific one with a radius of exactly 1. That's it. That's the unit circle. By doing this one simple thing, we anchor our triangle to a system that can literally spin forever.
And this move, it instantly makes everything so much simpler. See, because the radius is the hypotenuse, and its length is always just 1, those old SOHCAHTOA definitions just kind of collapse. Sine, which used to be opposite over hypotenuse, just becomes the opposite side, which is just the y-coordinate, and cosine becomes the adjacent side, the x-coordinate. We've gone from dealing with these clunky ratios to just, simple coordinates.
So, this is the golden rule. For any angle you can possibly think of, you just find where that angle's line hits the circle, look at the xy point, and bam! You have your cosine and your sine. An angle of 400 degrees, a negative 90 degrees, it doesn't matter one bit. The circle can handle all of them. This is the real breakthrough.
Okay, so talk is one thing, right? Let's actually see how powerful and, honestly, how intuitive this new system is. We're going to just run through 3 quick examples. All right, first up, what's the cosine of pi? Now, if we tried to use our old triangle method, well, it's impossible. You can't have a 180-degree angle in a right triangle. But with the unit circle, all we have to do is visualize it. We start at 0 and rotate 180 degrees, which points us straight to the left. So what's the coordinate at that exact point? It's -1, 0. And just look at how simple the answer is now. Cosine is just the x-coordinate, so the cosine of pi is -1. That's it. Done. No calculator, no complicated formulas needed. The answer is literally just sitting right there on the circle, waiting for us. Okay, next example. Let's say we're given a point. An angle, we'll call it theta, lands on the point -3/5, 4/5. And we need to find the tangent. Well, we already have our cosine, that's just the x value, -3/5, and we have our sine, that's the y value, 4/5. And since we know tangent is just sine divided by cosine, or y over x, the problem basically solves itself.
We just divide 4/5 by -3/5, and we get our final answer, -4/3. See? Once again, the coordinates gave us everything we needed to know.
All right, for our last example, let's switch things up a bit. This one's kind of like a puzzle. We're told the sine of an angle is 0.6, and we know it's in quadrant 2. We need to find the cosine. Well, we know that on the unit circle, x squared plus y squared always equals 1. So we can say cosine squared plus sine squared equals 1. Let's plug in 0.6 for sine, which gives us cosine squared plus 0.36 equals 1. A little quick subtraction, and we find that cosine squared must be 0.64.
So we take the square root of 0.64, which is 0.8. But wait, is it positive or negative? This is where that little clue about the quadrant is so important. In quadrant 2, that's the top left section of the circle, all the x values are negative. And since cosine is the x value, our answer has to be -0.8.
Now, before we move on, I want to address something that trips up so many people. Sine and cosine as x and y, that feels pretty intuitive. But tangent, it can feel a little abstract. So I want to give you a super simple visual way to think about it.
So what is tangent, really? I mean, yeah, we know it's y divided by x, but what does that actually represent when you're looking at the circle?
Here it is. This is the key insight.
Tangent is literally just the slope of that line going from the center of the circle out to your point. Remember rise over run from algebra? Well, that's just change in y over change in x. It's the same thing. So if the line is going up, the slope is positive, and the tangent is positive. If the line is going down, the slope and tangent are negative. It's really that simple.
So we've seen how the unit circle works, but why should you care? I mean, this isn't just some clever math trick. This complete redefinition of trigonometry is the foundation for describing pretty much every cyclical thing in our universe.
I mean, take the very device you're watching this on right now. It processes all kinds of signals, sound, light, Wi-Fi, using something called Fourier geometry. And the absolute core of that entire field is the idea that any complicated wave can be broken down into a mix of simple sine and cosine waves. The x and y coordinates from our little unit circle, they literally translate into a signal's phase and its amplitude.
So the real takeaway here is that the unit circle isn't some boring chart you need to cram into your brain. It's a fundamental tool. It's like a mathematical engine that lets us model and understand the rhythms and the cycles of the world all around us.
And that kind of leaves us with a final thought, doesn't it? We've seen how this simple circle connects the dots between geometry and sound waves. It really makes you wonder, what other complex parts of our world, from the stock market to our own brain activity, are really just simple waves in disguise, waiting for us to figure them out?